Applications of derivative. First, a rate of change. Suppose we have two quantities which are connected to each other and both changing with time. A related rates problem is a problem in which we know the rate of change of one of the quantities and want to find the rate of change of the other quantity. Let the two variables be x and y. The relationship between them is expressed by a function y is equals to the function of x. The rates of change of the variables x and y are defined in terms of their derivatives dx over dt and dy over dt. If dx over dt is known, we can determine dy over dt and vice versa. So we're now dealing with time. Any related rates problem can be solved as follows. First, decide what are the two variables describing your system or process. 2. Drawing a picture can often be useful. 3. Write an equation that relates the variables. To derive the equation, you may use a geometric fact like the Pythagorean theorem or similar triangles, a trigonometric identity, or a physical law. Number 4. Take the derivative d of dt of both sides of the equation. Number 5. Solve for the unknown rate of change. And 6. Substitute all known values to get the final answer. Maxima and minima. As an example, the area of a rectangular lot expressed in terms of its length and width may also be expressed in terms of the cost of fencing. Thus, the area can be expressed as a is equals to a function of x. The common task here is to find the value of x that will give a maximum value of a. To find this value, we set dA over dx equate it to 0. And we have steps in solving maxima and minima problems. First, identify the constant, say costing of fencing. Number 2, identify the variable to be maximized or minimized, say area or a. Then number 3, express this variable in terms of the other relevant variable or variables, say a is equals to function of x and y. If the function shall consist of more than one variable, express it in terms of one variable if possible and practical. Use the conditions in the problem. Say a is equals to function of x. And number 5, differentiate and equate to 0, or dA over dx is equal to 0. So these are the steps on how to find the maxima and minima. Example number 1. A ladder 13 feet long leans against a wall. The top of the ladder slides down at a constant rate of 12 feet per second. Find the velocity of the ladder when h is equals to 5 feet. So we have the length or the ladder, which is 13 feet, and when the height of 5 feet, we will find the velocity of the ladder with a constant rate of 12 feet per second when the ladder slides down. So we have the given. So the length of the ladder, which is 13 feet, and the constant rate, which is dh over dt, which is equals to 12 feet per second. And when the height approaches to 5 feet, we need to find the velocity of the ladder, which is dx over dt. Using the Pythagorean equation, so we have h squared plus x squared is equal to 13. And then we differentiate based on time. So we have d over dt of h squared plus x squared, and differentiate d over dt of 13 squared. And then we differentiate. So we have h squared, and it is 2h dh over dt based on time, plus the differential of x squared, it is 2x dx over dt, and the derivative of 13 squared is equal to 0. So 2h dh over dt transfer to other side, which is negative 2x of dx over dt, and cancel out 2 and 2, and the remaining it is h of dh over dt is equal to negative of x of dx over dt. And we're finding the value for dx over dt. So this is dx over dt, which means this is a negative sign of h over x and dh over dt. And this is the equation number 2. And this is equation number 1. At equation 1, h squared is plus x squared is equals to 13 squared. So we have the value for h, and we'll be substituting the value for x. So x squared is equals to 13 squared minus h squared, and x is equals to the square root of 13 squared minus h squared. And this is equation 3. From 3 to equation 2. And this is d of x over dt is equals to negative of h all over x, which is a 3 square root of 13 squared minus h squared, and dh over dt. dx over dt is equal to negative, and h is equals to 5, and square root of 13 squared minus 5 squared, and dh over dt, it should be negative because the rate of the ladder, which is sliding down, so therefore it should be negative sign, and we multiplied by the constant rate, which is 12, and equate that to negative times negative, it is positive. So 5 square root of 13 squared minus 5 squared, this is square root of 169 minus 25 and 12, and we have 5 square root of 169 minus 25, or square root of 144, this is 12 multiplied by 12, and we cancel out 12, and the value of dx over dt is equals to 5, and the unit, it is in feet per second. So this is the velocity of the ladder when h is equals to 5 feet. Example number 2. A kite 160 feet above the ground moves in a direction parallel to the ground at the rate of 5 feet per second. How fast is the string unwinding when the length of the string already let out is 200 feet? So we have a kite with a velocity of 5 feet per second from the ground, and the height from the ground is 160 feet. Of the string is 200 feet. How fast is the string unwinding? So we have given. The given is the height of the kite from the ground, which is 160 feet. The velocity dh over dt is equal to 5 feet per second. And when the length of the string, which is 200 feet, we will find the rate of the string ds over dt. We need to use the Pythagorean equation. So this is Pythagorean equation, which is h squared plus x squared is equal to s squared. H is equals to 160 feet, so it's 160 squared plus x squared is equals to s squared. And then we derive at t or time with 160 squared plus x squared is equals to derivative of s squared. So derivative of 160 squared is 0, constant, and derivative of x squared, it is 2x dx over dt, and it is equal to derivative of s squared, which is 2s ds over dt. ds over dt, and this will be cancel out the constant 2, ds over dt, it is equal to x over s of dx over dt. So this is equation 2, equation 1. At 1, so this is s squared, it is equals to h squared plus x squared, or this is 160 squared plus x squared, and we need to find x, which is s squared minus 160 squared, or x is equals to the square root of s squared minus 160 squared, and this is equation 3. Substitute equation 2 or equation 3 to 2. So equation 2, substitute equation 3 to 2. We have ds over dt, which is equal to the square root of s squared minus 160 squared all over s multiplied by dx over dt, and we substitute the value for s and dx over dt. The length of the string, it is 200 squared minus 160 squared, and we divide by s, which is 200, multiplied by the dx over dt, which is 5, and this is equivalent to square root of 200 squared minus 160 squared, it is equivalent to 120, and we divide by 200 multiplied by 5, and ds over dt, it is equivalent to 3 feet per second. So this is the rate of the string unwinding when the length of the string is 200 feet. Example number 3. A triangular throw 10 feet long is 4 feet across the top and 4 feet depth. If water flows in at the rate of 3 cubic foot per minute, find how fast the surface is rising when the water is 6-inch depth. So we have a triangular throw and the length of the throw is 10 feet with a top base of 4 feet and the depth is 4 feet. And the rate or the water flowing with a rate of 3 cubic foot per minute, and we need to find how fast the surface is rising if the depth of the water y, which is equal to 6-inch. The volume of the water, so volume of water, it is equivalent to v 1/2, which is triangular, of x times y and the length, which is 10, or v is equals to 5xy, and this is equation 1. Once we have the equation 1, next we need to have the cross section of the triangular throw, and we have the 4 feet top base and the height, which is 4 feet, and the height of the water, which is equivalent to y, and the top base of the water, which is x. And using the similar triangle, so we have x, the small triangle, over y is equal to the big triangle, which is 4, and the height, which is also 4, and cancel out 4. The value is x is equal to y, and this is equation 2. From 2 we substitute to equation 1, so we have volume and we have 5 of y, and we change x to y, and this is volume is equals to 5y squared, and that's the time we need to differentiate verse based on time. So dv over dt is equals to 5 times 2y and derivative of y, which is dy over dt. When y, the height of the water, is equal to 6-inch, and then we change to inches to feet. So 1 foot is equals to 12 inches. So 6-inch over 12-inch, it is equivalent to 0.5 foot or feet. So we have the height of the water, it is equals to 0.5 feet, and we substitute the value to equation 3, and we're finding the dy over dt. So from derivative of the volume over time, which is equivalent to 3 cubic foot per minute, is equal to 10, and the height of the water, which is 0.5 feet, and the unknown, which is dy over dt, and dy over dt is equal to 3 over 10 times 0.5, and the value, it is equivalent to 3 over 5 or 0.6, and the unit, it is in feet per minute. So this is the rate of water. Example number 4. What positive number added to its reciprocal gives the minimum sum? So we'll be using the maxima and minima. So let x the required positive number. Next, the reciprocal, which is 1 over x, and this is the reciprocal of the number. And we presume that y is the sum x and the reciprocal 1 over x. So we have solution. So we have the solution, which means y is the sum of x plus 1 over x. And then you change first, so y equals to x plus 1 over x is also x negative 1. And then that's the time we derive. So y will be y prime, and derivative of x, it is 1. And then derivative of x negative 1, it is negative 1 of x negative 1 minus 1, or negative 2. And this will be y prime is equals to 1 minus 1 over x squared. The value is minimum, so therefore y prime is equal to 0, or this should be 0, 1 minus 1 over x squared. And 1 over x squared is equals to 1, or x squared is equals to 1, or x square root of 1 is also 1. So this is the value. Example number 5. A rectangular field of fixed area is to be enclosed and divided into 3 lots by parallels to one of the sides. What should be the relative dimensions of the field to make the amount of fencing minimum? So we have the rectangular field, and we designate the length, which is x, and the width, which is y, and we subdivide into 3 equal lots. So we have 1, 2, and 3. So the area of the rectangular field, it is equivalent to the width and length, or x times y. It is equal to, this is product rule, so x of y prime plus y, derivative of x, it is equal to 1. And the value for a, which is in minimum, and the value is 0. So equate that to 0. And we have xy prime plus y is equal to 0, or xy prime is equals to negative y, and y prime is equals to negative y over x, and this is equation 1. Next, using the fence perimeter, so we have P, and the perimeter fence, we have x twice of x plus the y value. However, we divide it into 3 equal parts, so therefore we have 1, 2, 3, and 4 y's, or width. So we have 4 y, and we differentiate. So this will be dp over dx, and Derivative of 2x, it is equivalent to 2 plus 4. Derivative of y, it is y prime. Based on minima, the value is 0. 2 plus 4y prime, and it is equal to 0. And this will be equation 2. We substitute equation 1 to 2, and this will be 2 plus 4 y prime, it is negative y over x, and this is equal to 0. 2 is equal to 4 y over x, and we cancel out 2, this will be 2, or x is equals to 2y. Therefore, length is twice of the width. So this will be the answer.